about the convolution segmentation of textual images. And I will work within the framework of a Bayesian approach and a hierarchical Bayesian approach. And it will allow for optimal estimation, optimal decision, and it will be computed by stochastic sampling. It is a common work with Cornelia Vakaridis, one of my PhD students. Thank you again for the organization of this seminar. So first, I directly mention a few applications of these works. We have a lot of application of imaging in astronomy, or more generally in physics, also of course on medicine, computer vision, a lot of activities regarding knowledge, health, industry, applications, fields of these imaging problems. Also a lot of modalities, for example, magnetic resonance imaging, echography, radars, a lot of acquisition modalities, often in relation with interaction between a wave and matters, maybe electromagnetic waves or ultrasonic waves and so on. And regarding signal processing or data science problems, we face denoising, deconvolution, Fourier synthesis, for example, interpolation, extrapolation, that are standard signal process problems. And we also have additional problems, for example, segmentation, that I will talk about. It could be detection of impulsions, classification, and so on. And in addition, estimation of additional parameters. I would detail that later on. For this presentation, I will deal with deconvolution, interpolation or extrapolation, and segmentation and estimation of some hyperparameters. Maybe you could feel free to interrupt me and ask a question, or we can have question at the end of the talk, of course. To introduce some notations, this is a standard slide. Y is the observed data, observed image. X is the unknown image. Practically, this is not given. It is known because it is a simulation example. And this model's observation system. We have, let's say, data part, for example, convolution and noise. And this is a model for an observation system. It models, for example, blur, noise, mixing. And what is the object of this problem? What is the object of this talk is the idea of estimating the input given the output and maybe some other information. But the idea of finding an estimation function that for a given set of data produces an approximation or an estimation of the unknown. Here again, this standard question. Usually we have an ill-posed problem. We have an inverse problem that is often ill-posed. It means that in the observed data, information regarding the input is missing. It is because of degradation, for example, limit in resolution or attenuation of high frequencies and so on. That's why we resort to what is called regularization. It means accounting for prior information to compensate for missing information in the data. And it gets two specificities. The first one is the specificity of the inversion method. I mean that it is difficult to build an inverse method that will apply to any problem because it is specific to the information that is accounted for. For example, textures or positivity or smoothness or contours or specific prior information that is accounted for to compensate for missing information. And the other idea is the idea of compromise. Since we have two sources of information, one coming from the data and another one coming from prior information to compensate for missing information, we have two sources of information, and then we have um, a compromise to strike tuning parameters. This is the same slide, the same idea than previously, but regarding advanced question, I mean regarding extra parameters. The first one is the parameter that I mentioned on my previous slide regarding compromise between data and prior. It means that we have something regarding level of noise or level of image that strike the compromise between them. And we talk about unsupervised or unsupervised problem or self-activity, self-tune methods. The second type of parameters, the golden parameters, constant, for example, instrument parameters. Think about convolution with a Gaussian blur, and the size, the width of the Gaussian is unknown. And we talk about myopic or self-calibration or maybe blind problems. And the third one is the green one. It is about extra parameters. For example, to model edges, peaks, regions. It is about hidden variables, and we talk about augmented problems. For my talk, it will deal with labels to model image segmentation. And we also have an additional problem that I will not talk about that in this talk. It is in relation with model selection. I mean that, for example, we can imagine that we have several possible models for noise or several models for points for instrument, for example, a Gaussian blur or Lorentzian blur, and we need to select a good or a correct model in addition to parameters, but this is not the idea of that talk. I will talk about hyperparameters and hidden variables label in that talk. I will skip this one. I could be back to this one. It gives some historical landmarks. This is an idea of a specific application possible for this talk. It is a kind of a natural image with various kinds of cultures of agronomical image, and more specifically with oriented textures. That's one of our possible application of this specific talk. Anyway, the problem that is addressed is the one, as announced, about texture images like this one. It has specificities. We have a piecewise homogeneous image, and the piece will be modeled by label in relation with segmentation. And each part is a specific texture image that is modeled. I will see, I will give the data later on, parameterized with some texture parameters. And then this is about the observation system. We have a convolution that produces a blur. And we also have a truncation. I mean that some data are missing, and we have noise. Okay, now I have my outline. I will present models for the image, for the texture, and for the labels. And then I will give details about observation system. And then I will mention a hierarchical model that allow for modelization of dependencies and independencies of variables. Then I will give the joint distribution for the data and the unknown parameters. And then I shortly introduce the idea of optimal estimation, and I will concentrate on computations. And it will rely on stochastic sampling and empirical estimates from the output of the stochastic sample. And then I will give a first numerical assessment. So first of all, model for image. And first of all, for texture images. The texture images will are modeled as simple zero mean Gaussian fields with a specific correlation. This is a correlation matrix, the covariance matrix, and it is parameterized by two parameters. One is a scale parameter, and the other one is a texture parameter. So the probability density function for the image, given the scale, the level parameters and the texture parameter, is in that way. It is a Gaussian model. And then I will be interested in stationary and more specifically in circulant stationary model. So I will be able to write the probability density function of the image as a function of the Fourier coefficient of the image. This is a Fourier transform, or let's say the fast Fourier transform, the discrete Fourier transform of the image. And we have a very simple model that is separable with frequencies, index P, and this is the frequency running for all the frequencies of the image. And we have a Gaussian model with variance in the Fourier domain that is parameterized by a specific function, itself parameterized by theta, that are the textual parameters. And I have such a model for capital K images. This is an example. Oops. I have a Laplacian power spectral density in that form. It is parameterized by the parameter theta, for example, the central frequency and the spectral width. For example, that one. This is the power spectral density, this function. And this is a realization of the Gaussian model with that power spectral density. This is another example, another one. And depending on the parameters, I have more or less high frequency in the texture, more or less wide spectral content. For example, this is the null frequency, and this is a kind of low frequency noise. This is a case not described here with two, and then a kind of crossing texture. Anyway, it is this kind of model that I will use to in talk. That is the model for images, textual images. That is a model for the label that will account for the idea of homogeneity. I mean that neighbor pixels are likely probably to have the same value. It will allow for the segmentation. It is modeled, it is denoted L sub P for the label of pixel P. I have capital P pixel and K classes, and then each label takes a value in this set. And then I will use a very standard Markov field, more specifically a POTS field, with this probability density function. And this probability density function rely on this new oval that just count the pair of neighbor pixels with the same value. It is a kind of parsimony of the gradient of the label image. It quantify the homogeneity or the length of the contours. Okay. And this is a probability density function. It involves it's called a POTS parameter that we could say a kind of correlation parameter that tunes the mean number of the size of the region. I will give an example on the next slide. And what is important is this constant, this normalization constant of the POTS field. It is important because I am interested in automatic tuning of the POTS parameter. So I need this probability density function normalization constant. Okay, this is two examples, one for 2 classes and one for 3 classes with various value of the POTS parameter. For the new value of the parameter, I have a white noise, and for larger value of the POTS parameter, I have larger size of homogeneous region. A few words about this normalization constant. It could be computed so that the summation over all the configuration of the field, the probability density function, the probability function sums to 1. But it is a summation of a very, very large number of configuration. Of course, each label could take k value, so it is a very, very large summation. And we are able to approximate. I will not give all the details about that. I could answer your question if you have. I could approximate, we could approximate this probability density function as an expectation. And we have computed, pre-computed this probability, this normalization constant. And we have these normalization constant. It is the normalization constant, the log normalization constant, are the function of the value of the POTS parameter for various size of image and various number of classes. And this is a derivative of this function. It is a second derivative of this function. For similar functions here, we have the same number of classes and various size of image. Okay, anyway, I can consider that I have this normalization function, normalization constant, as a function of the tuning parameter. So I will be able to estimate this parameter also. Okay, now I have my model for textures, Gaussian models. I have my model for labels, and then I can build this kind of patchwork, picking correct pixel depending on the value of the label. I can build this kind of patchwork. It is this formula. This is the image. This is this image based on part of these ones. And these are diagonal matrices with 0 and 1, depending on the constant P is in the class K or not. And then it picked the correct pixel in the correct image to build this patchwork. And this patchwork is the unknown image. And these things are models for the unknown image. Okay. Then a few words about the observation system. I already mentioned that, in fact. I have a convolution, okay, that produces a blur. A truncation that models the idea that some pixels are missing, and noise. And then I have an observation equation. Y, the unknown image, is based on the true unknown image and a convolution and a truncation plus noise. Okay. And then I also have a model for noise. It is a simple zero mean Gaussian wide noise with a parameter that is denoted by gamma sub noise, this probability density function. And then I also have some prior distribution for the other unknowns. For example, the Potts parameter. I have for the Potts parameter a uniform probability density function between 0 and a maximum value. In my simulation, I selected 3. We also have uniform priors for textual parameters. For example, the frequencies of the oriented texture. And we also included prior information for the gamma parameters, for example, the noise parameter or the scale parameters for the unknown images. And these ones are rather poorly informative parameters, prior for the hyperparameters. Very large, poorly informative priors. Okay. Then I will give the rather standard natural hierarchical model. It models all the dependencies and dependency, more specifically conditional dependencies and dependencies of the various variables, the unknown image, the label, the parameter for noise, the texture parameters, the Potts parameters, and based on the previous models and this hierarchical, we are able to build the full probability density function, including the data and all the unknown parameters. It is based on likelihood, priors, and so on. And we now have a full probability density function for everybody. And then we have posterior distribution, conditional posteriors, and all the other possible probability density function can be deduced from the full joint probability density function. Then I have 2 slides that I will not comment in detail that are in relation with standard Bayesian strategy. I mean that we are interested in building a decision or an estimation function phi. We rely on a cost function and then on a risk function that is an expectation of the cost function and an optimal estimation or decision function that is the one minimizes the risk, that is an expectation of a cost function. And typically for estimation of regression problem, I mean continuous parameter, if we select a quadratic cost, it is known the optimal estimation function is a posterior mean. And for decision or classification, for discrete parameters, and for a binary costs, I mean 0 if the decision is correct, and 1 is I have an erroneous decision, then the optimal decision function is a posterior maximizer. That's why I am interested in posterior and computation of maximizer, or maybe marginal maximizer, I could comment that, and posterior expectation. That's why we are interested in sampling. To compute this estimate, we will resort to sampling. Practically, it says that we are interested in producing a large number of samples of all the unknowns under the posterior, and then compute empirical mean to approximate expectation, posterior expectation, that is minimum mean square error, that is the optimal estimate, and to compute empirical marginal maximizer, that is in fact the idea of building marginal histograms and select the most probable value for the labels to produce the segmentation. And then we are interested in the idea of producing samples. Of course, the direct sample is not possible because we have a very intricate probability distribution. That's why we resort to Gibbs sample. The Gibbs sample allow the to starting from a global problem to produce split in sub problems that are simpler. And we resort to standard sampler for some parts. We will resort to inverse cumulative density function for other parameters, and Metropolis Hastings sampler for another part of the parameters. I will detail that in the next slides. I will detail that for all the parameters. The idea of the Gibbs sampler is to sample each parameter one after the other, each under its conditional probability density function, or each under its posterior probability density, conditional posterior density probability, given the other parameter. And I will comment, at least shortly, each of these probability density functions. The first one is for the noise parameter. I need to sample under the probability density function of the noise parameter, given all the other parameters. And it is proportional to the joint probability density function. So I just need to pick in that the factors, and I have two of them, the factors that are depending on gamma sub noise. And then I have one coming from the likelihood, this one, that itself comes from the noise probability density function, and the gamma prior probability density function for the gamma sub noise. And then we easily see that the idea of conjugacy. We easily see that we have a gamma probability density function. And we have two parameters for this gamma probability density function that can be computed easily. This is a number of data, and this is the adequation to the data term, data minus output of the observation system for a given image, for in fact the current image in the Gibbs sampler. We have similar result for the scale parameters of all the texture images. We have two factors in that, one coming from the prior of the unknown texture images, this one, and one from the prior for the scale parameter itself. This is the part coming from the prior for the unknown image. This is a part coming from the prior for the scale parameter. And we see again that we have a gamma distribution. Again, it is expected from the conjugacy idea. And we have a gamma probability density function and two parameters, one in relation with the number of pixels and another one in relation with a quadratic norm that can be computed in Fourier domain. That is a kind of norm of the unknown image, the current unknown image within the Gibbs sampler, and it is a weighted norm, the weighted depending on the value of the textual parameters. Okay. Then next one is a label. The label, I need to sample that under the probability density function of the label given the other ones. It is proportional to something coming from the likelihood, this one, it is this one. It involves the patchwork that is built depending on the value of the label and the Potts model. And then for one pixel P, the label take the value K given all the other parameters and all the other label that can be easily computed. It depends on the number of pixels neighbor of the current pixel with the value K and something coming from the likelihood that amounts to test for the current pixel the value of the adequation term that is here if the current pixel is in class 1, class 2 till capital K, class capital K. And we have a very fast way to compute this one. Okay. That's the idea of computing the sampling for the label. Okay. Next one is the true image itself. The capital K true image, complete true image, unknown true image. We again have two factors, one coming from the likelihood, another one from the prior for the texture image. We have a Gaussian model. We have a Gaussian model with these covariance, in fact, this inverse covariance and this mean. And we have a simple Gaussian model, but large dimension one. So it is not so easy to compute a sample of this large scale Gaussian model. And we have standard approaches relying of factorization, for example, of the covariance or the inverse covariance of precision, or diagonalization, or and so on. But we resort to specific efficient algorithm that rely on perturbation optimization. It means that we are able to produce a criterion with a precisely designed stochastic perturbation so that the minimizer of the criterion is a sample of the probabilities and sample of the Gaussian of interest. And then we included that in the algorithm to produce a sample of each of the capital K images. Okay. Then what about the texture parameters? Texture parameters are in the model of the unknown images and in the prior for the textual parameters. And regarding the prior, we have uniform priors, okay. Regarding the likelihood, regarding the prior distribution, we have a kind of intricate dependency because the textual parameters are in the power spectral density function. Think about the Laplacian power spectral density function that involves the central frequencies and the width. So there is a very intricate dependencies. So we resort to a specific Metropolis hastings step, and it is based on what is called MALA, and improved version of Metropolis hastings adjusted Langevin algorithms with directional proposal for the Metropolis hastings, and especially one that rely on the Fisher information matrix, because in fact it is relatively easy to calculate the Fisher information matrix for these parameters. Okay, and then we have a relatively fast sampling algorithm for these parameters. And the last one, this is some details about the Metropolis hastings algorithm. I could give details, or I guess you know about that. The last one is the POTS parameter. The POTS parameter, of course, is in the probability density function of the label and the prior one. The prior one is just uniform distribution between 0 and a maximum value that I set to 3 in the simulations. And of course, it involves this part, relatively easy regarding the dependency with the POTS parameter, and this one that is more difficult, that is the partition function, the normalization constant that we pre-computed. And based on this pre-computation, we use a sampling of this parameter based on the inversion of the cumulative density function. It is to sample a value u uniformly between 0 and 1, and then compute numerically compute the inverse of the cumulative density function based on the pre-computed value of the partition function, the normalization constant. Okay, that's it. Now I have described all the sampling steps, and I can give a first numerical assessment. It is a toy example. This is a true label with 3 regions, 1 black, 1 white, and 1 gray. I must say 3 classes rather than 3 regions. This is a true image, and it is the data. In that illustration, I have no convolution. I just have missing pixels and noise. We, of course, have result including convolution in the paper. Okay, and then based on that, we have running the Gibbs sampler, and I show here 2 of the parameters, the noise parameter and the POTS parameter. And we have, of course, a true value for the noise parameter, and we estimate something that is rather near the true value, and we have an estimate of the POTS function, but we do not have a true value of the POTS function because we do not compute a realization of the bots function or the bot field. And it is about only 1 minute of computation. So it is rather fast algorithm, given that we sample the label, the texture images, the texture parameters, and the noise level, and so on. A lot of parameters. And it is MATLAB code that just run for 1 minute. Okay. And this is the estimated label. So we have a rather correct classification, less than 1% of misclassification. And what is here is the location of the misclassification. I am in a simulated context, so I know the true label, so I'm able to characterize a correct and erroneous classification for each pixel. This is the location of the misclassification given the true label. And this is the probability of the label that is computed only starting based on the data without this one. The algorithm produces an approximation of the posterior marginal probability for each label. And it says that the algorithm is able to quantify, in one sense, the uncertainty. And we see that most of the misclassification are located in a place where, in a location where the probability is low. So the algorithm, the method is, in one sense, able to give an idea of uncertainty, and low and a high uncertainty is in correct adequation with misclassification. A kind of indication or kind of warning of misclassification. Okay, and this is the estimated image. This is a true one. This is the data, missing pixels and noise, and this is the estimated image. We have correct estimation of the unknown image. In the paper, we have produced precise quantification of errors. Okay, we also have posterior standard deviation or credibility intervals to assess uncertainty quantification. Okay. And this is my last slide. The conclusion, I propose here synthesis. So we address the problem of both convolution segmentation, joint deconvolution segmentation of piecewise texture images with a triple difficulty: convolution, missing data in noise, including, this is something important for us, including estimation of all the hyperparameters, including the post parameter. And we developed a Bayesian approach. Something that is important in my opinion is that we have a kind of optimality of the estimates, and we also have convergent algorithms. The Gibbs sample is guaranteed to produce samples under the posterior, and the empirical mean empirical histogram are guaranteed to convert to expectation and probability and so on. And we have a first evaluation. We have some other evaluation in the paper. Okay, and we have some perspectives. Ongoing inversion segmentation, something else than convolution, for example, radon for scanners. And of course, Ali has a lot of papers about this idea of inversion segmentation, including convolution deconvolution segmentation, tomography segmentation, and so on. We plan also to go to non-Gaussian noise, and we plan to include non-Gaussian models for noise based on latent variables. I mean that modeling non-Gaussian noise through Gaussian noise conditionally to some latent variables, and then marginalization of latent variables. For example, Gaussian noise can be most a mixture of functions. It could also include correlated noise. We also plan to, we have started this part, to estimate some parameters of the point spread function for the instrument. Also, the idea of model selection, for example, is automatically selecting the number of classes. And of course, to go to, we have started this part in a different context, application to real data. That's it. So I thank you for your attention. And of course, if you have a question, I will try to do my best to answer your question. Thank you.
Thank you, Jean-Francois. It was a very, very rich presentation. I almost have questions on every slide. So there are many points which are very original and very interesting. But first, let to know if there are questions in the audience, and then I will come back to my questions. Any questions in the audience? Or
hello, Professor.
Yes.
Yeah, I have several questions. It's a very interesting work. I saw you used many different sampling methods for different variables and hidden variables, and because I haven't looked in detail the details for all the how you say demonstrations. So for example, in the slide 34, could you please return back to slide 34? It's very interesting that you use the sampling method for high dimensional image. Yes, the perturbation optimization. Could you give more details about that? I didn't quite understand the detail of this sampling method.
I didn't give the details. I will try to give some more and to drive to a paper that describes that. Let me mention first that we have a Gaussian model because we have a linear system and a Gaussian noise and a Gaussian prior. So we are able to compute the mean and the covariance or the inverse covariance of or the precision of the Gaussian that we need to sample. And for this part, we have something coming from the prior that is stationary and that can be computed, manipulated in the Fourier domain. From this one, from part of this one also, this is a convolution matrix, so we also have possibility to manipulate that in the Fourier domain. But due to the truncation and due to the selection of pixels in one class or in another one, this breaks the stationarity, this breaks the circular structure. So this cannot be manipulated easily in the Fourier domain. But we have kind of blocks, and some part of that can be computed through filtering, through fast Fourier transform, through discarding missing pixels. I mean, for example, for one image, I can compute that, or I can compute the transpose of that. I mean that it is easy to compute the gradient of that, in fact. Okay, that's a first ingredient. Then, since the covariance has no stationarity, no circulant structure, it is not easy to use this possibility. For circulant matrices, for example, it is easy to produce a factorization, a diagonalization in the Fourier domain. It is not possible here. So we resort, in fact, in something that is similar than that. Maybe we can have an idea that sampling a Gaussian is something equivalent to filtering a white noise. Or it is also equivalent to solving a linear system. And then it is also equivalent to minimization of a quadratic criterion. I mean that minimization of a quadratic criterion is just equivalent to solving a linear system, is just equivalent to diagonalization of or Cholesky factorization of a covariance. That's in fact the key idea. The idea is to build a criterion, a quadratic criterion, so that the minimization of the criterion produces an optimum that is the minimizer of the criterion, that is a solution of a linear system. That is a solution of a Cholesky factorization. That's why it is possible to build a criterion including a perturbation of various terms. In fact, it is a consideration of this criterion and introduce a perturbation including noise or including realization of the prior model to build a criterion so that the minimum of the criterion is a sample of the Gaussian with the correct mean and correct covariance. Maybe we have a paper on my web page. I don't know if I can shortly change that. Maybe I can find that shortly. Yes, this one. I will try. Yes. Up, 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 up. This is a paper that is on my web page. It describes what I am talking about. Just sorry. Yes, it is very similar to what we have here. Sampling a Gaussian, including that. And then we have that. And then we build a perturbed criterion that will allow for sampling, automatically sampling what is required. This paper gives all the details.
Okay. Okay, I'll look in details in that. Yes, I see. I think it's something, it's kind of like you used the correlation between the optimization method and statistic method. So use some optimization method to approximate the sampling method, right? If I understood correctly. Okay, I look in details.
But what is important is that, in fact, from one sense, there is no approximation. I mean that the minimizer of the criterion is exactly a sample of
Exactly.
the
Okay.
Gaussian. But
Mm-mm.
there is a kind of approximation because we use gradient algorithm to minimize a quadratic criterion, and then we do not have practically the exact minimizer of the criterion. So there is a kind of approximation because the optimization is total optimization, but the minimizer is exactly a sample of the correct probability.
Of the sample. Okay. I see. Thank you.
Welcome.
And
Welcome.
in slide 27. So, yeah, you showed that slide very fast, and I didn't.
Yeah.
27.
I will comment the 26 and the 27.
Okay, thank
it
you.
is welcome. It is in fact nothing new in that. It is just in relation with a basic standard Bayesian strategy. We are interested in building an estimation function phi so that for one data set, we have one estimate. Okay. And then to do so, we consider a cost function. These are two values of the unknown parameter, p. For example, norm between p and p prime. This is what is called the cost function in the Bayesian strategy theory. And it is an expectation of the cost function. This is the parameter. This is the estimated parameter. Think about that as the parameter and the estimated parameter. The cost function. And this is an expectation. It is an expectation regarding the joint law under the data, y, and the unknown parameter jointly. The joint probability density function for the unknown and the data. And the expectation of the cost function. So it is a function only of the function. It is a risk associated to the function phi. And then we naturally, the Bayesian strategy, naturally select the estimation function or the decision function that minimizes this risk. It is the optimum function over all the possible functions.
Yes.
And then often for continuous parameters, if we consider the cost function as the difference, the squared Euclidean norm between two parameters, the optimum function is known to be the expectation, the posterior expectation. It is the best function, the minimum mean square error. And regarding discrete parameter, we have a decision. If we consider this cost function, I mean that if the decision is correct, there is a null zero error. If the decision is incorrect, it costs 1. For this binary cost, the optimum function is the posterior maximizer. It says that among all the possible functions, I should add opt here. It is an optimal function, opt. The optimal function, the one that minimizes the risk. That's why we select the posterior mean and the posterior maximizer as estimate for the texture images, for the parameters, and so on. And this one for the label. But in fact, I must mention that practically we do not compute the maximizer. We do not compute the posterior maximizer. We just compute the marginal posterior maximizer because it is easier to compute. Based on the samples of the Gibbs sampler, I can easily compute the marginal posterior maximizer not really the posterior maximizer. That being said, that's why we are interested in this thing, because we have optimal estimate. Is that an answer to your question, or?
Yes, I just want, because I'm not, it has always been a question for me, because for the discrete parameters, I understood that why we use the maximizer for the posterior distribution, but for the continuous parameters, why should the mean posterior be the optimal estimation function? Because we can, for example, we can also use the maximum of the posterior, or so how should we choose, for example, to use mean value or the maximum value?
I really do not have strong argument in favor of one or of the other. I think that this is an interesting way of quantifying the error. That's why I selected this one. But of course, we could want to compute the maximizer. But another argument is a practical one, is that we have a Gibbs algorithm, and based on the output of the Gibbs algorithm, we are able to compute the empirical mean and then the posterior mean. It could be rather difficult to compute in that case. The joint map, of course, could code iteratively conditional maps, but not sure that it will converge to the joint map. In that case, we have convergent computations. I mean that the expectation converges to the empirical mean converges to the expectation, and the Gibbs samples, the distribution, the probability density function for the Gibbs samples converges to the posterior. That's why we prefer these ones.
For the sampling method, yes, it's better to use the mean value of the expectation of the posterior distribution.
Yes.
Okay, thank you.
Of course, we have
that's all my
other existing algorithms, let's say, to compute the maximizer, but probably no guaranteed. And we also have a lot of variational base idea, and Ali and some of his worked a lot very interesting papers about that.
Yes. Okay. Thank you for your answer. That's all my questions.
Thank you for your question.
Other questions in the audience?
Professor, I may have one question. So in the sampling method, in the development of sampling method, there one direction, they introduced the dynamic system method to design sampling paths. For example, they used the Jacobi-Hamilton dynamic system to design the sampling process. Professor, can you give us some comments about this direction, this research direction, as compared with your research? So thank you.
Welcome. I will try to do that. I will just remind that we are interested in the textual parameters. I would like to take a few seconds to remind that. For example, that is a model for the unknown image, the texture image. That is a model for the texture, and the texture parameters are these ones. Central frequency, this one, for example, it is Fourier domain, and central width. So the unknown parameters are within the unknown texture parameters are within the probability, the power spectral density in that exponential modeling the Laplacian decreasing. And in that functions. So we have really a very intricate dependency. But we can calculate, for example, the gradient, the derivative of that with respect to each component of the parameter theta. We can also compute the second derivative and also the expectation of the second derivative in relation with the Fisher matrix and so on. So it is very intricate, but we can calculate the gradient. That's it. And then take advantage of that to propose, let's say, interesting sample within metropolis hastings. The standard, I guess you know about the standard metropolis hastings with a proposal and a probability, an acceptance probability. And this proposal is very important because depending on the proposal, we will have a low or high acceptance probability and large jump within the parameter space. And then we started to use, let's say, standard random walk, and then we had a lot of rejection and a very slow algorithm. And then we turned to these directional algorithms. And as you mentioned, we have Hamilton possible sampling. In that work, there is no Hamiltonian sampling. In that work, there is only a kind of Langevin algorithm. And then the Langevin, not just Langevin algorithm, but an extended version of the Langevin algorithm. The Langevin algorithm only take advantage of gradient, and then we took advantage of the gradient and the Hessian. When taking advantage of the Hessian, it is not a really good idea because in some iteration, the Hessian is not a positive definite matrix. On the contrary, the Fisher matrix is a positive definite matrix everywhere. That's why this is a better idea than this one. And then we selected a direction for proposal, that is the inverse of the Fisher matrix times the gradient. Maybe I can also try shortly to share another paper. Just let me a few seconds. I think I will be able to find that shortly. Yes. This paper, let me check. Yes. Let me share this one. It's another paper on my web page. It is devoted to another problem. It is based on a model selection and texture classification, but it is based on the same model. the same textual model, so we have things about model selection, but regarding the sampling, we have the same model for the image and the sampling of the textual parameter. We compute the Fisher information by derivation of the log of the probability distribution. Excuse me, maybe, yes, we have this Langevin algorithm, extended Langevin algorithm. This is the log probability density function. This is the inverse of the Fisher matrix, and this is the perturbation of the algorithm. This random walk, a Gaussian random walk, this is a Gaussian, with a mean that relies on the gradient and the inverse of the matrix. Okay, it's maybe a part of an answer to your question. And this is this is a comparison of convergence. This is a convergence of the standard for one parameter, the standard random walk, and this is a convergence for the Fisher random walk. We have a very faster convergence because we take advantage of the gradient and something regarding the second derivative, not the Bayesian, but the Fisher information matrix. Is that an answer to your question, or maybe I misunderstood something?
Yes,
or...
it's very clear. Thank you, Professor. It's very clear.
Welcome.
Thank you, Rayo. Okay.
Other comments or questions? Okay. Yes. Your microphone.
Yeah. Bonjour.
Bonjour.
May I ask one question? Yeah,
Yes,
it's very nice to hear from you. So,
thank you.
For your examples, you give us small size of image. So yes, like this one. So if we 10 times of the size of image, at the same time, the gradients information is not so clear. For example, in the real applications in remote sensing, in that case, how could we trade off the precision and the reliability using Metropoly-Hastings method?
Not sure to understand. You talked about larger images?
Yes, large size and the low quality of gradients.
Low quality of gradients. You mean
yes.
Gradient?
The border of the image is not quite clear, or the image contrast is not so vivid.
Yeah, I think that
for example,
he's talking about infrared images. Where,
yes, all remote sensing images.
Where the boundaries of the different regions are not very sharp.
Yes, okay. The boundary is not sharp at all.
Okay, thank you. Vivid.
Smooth.
Yeah, vivid, sharp. Yeah, okay. Yeah. Let me say that it is a toy example. It is the label. It is the true image. In the true image, we have sharp edges by construction in the true image. This is observation without convolution. It is just missing pixels. So in fact, in that case, we have sharp edges in the data and just missing pixels. I will try another paper. I will share another paper. The paper in relation with this talk, that is this one, in which we have blur, and then we have unsharp edges. this is the paper in relation with this talk.
Yes. I saw this one in your email.
Yeah, and then this is the same idea than in my talk, but in the examples of this paper, we also have blur. Maybe not in that example.
Yeah.
Yes, for example, in that example, we have, this is a true label, this is a true patchwork, and this is the blur and noisy. And then thanks to the fact that we jointly estimate the image and the label, we are able to sharpen the edges. I mean that, of course, it could fail, but when we estimate the label, if we have sharp edges, because we have a correct deconvolution, it is easier to estimate the label. And if we have correct label, it is easier to produce a deconvolution. Okay, so one of the advantage is that we jointly produce deconvolution and segmentation, so that even if in the data we have blur, we are able to separate, to segment, and to sharpen edges. Is that an answer to your question, or?
Yeah, I can understand. Yes, that this is a good way to do so. Yeah, I will read this paper carefully. Mm-hmm.
Yes, in that example, I think we have blur and noise, but no missing pixels. And in that estimated image, we have sharpened edges with respect to this one. So we partly restore sharpened edges that we have in the true image. For example, here, in that case, whereas in the data we have blur. Of course, if we have very strong blur, maybe it will not work, depending of wavelengths, depending on optic, depending on physical parameters. It could be enough or not, I don't know. I have no answer specifically regarding infrared images.
Mm-hmm.
That's,
but at least we can estimate the error that for the border area, that how, to what extent we can give a precision, the confidential interval. Yeah.
Yes, that's one of the advantage. In that example, that is a simulated one, as I mentioned in the talk, we were able to locate the misclassification and jointly, without the ground truth, to have a probability for each, a marginal probability for each label, so that a kind of uncertainty quantification.
Yeah, so I also very interested in the framework. How could we accelerate the method you propose in industry imaging? For example, in your talk, you talk about all the calculation consume 1 minute. But if the size of image is very large, like 1,000 times 1,000, so how about your, I mean, the calculation efficiency?
Yes, it is only 1 minute. Several comments. First comment is that it is 1 minute for that case without convolution.
Yeah.
Because we are able, when sampling the labels, to produce parallel sampling, because we have conditional and dependencies in relation with the Markov property of the POTS model.
Yeah.
That's the first point. It is longer than 1 minute when we deal with convolution, because we have extra correlation, additional correlation between the label due to the point spread function. That's the first thing. But we have, for example, all the sense and Wang algorithm or things like that to accelerate the computation of the sampling, even if we have convolution. Anyway, if computation time, since of course the computation time increases with the size of images, of course. We do have approximation, for example, variational Bayesian variational approximation to compute that, maybe probably very fast computation. So as expected, accepting approximation of the posterior, we could have very fast algorithms. So my opinion in that, if this algorithm is not fast enough for one given application, we do switch to faster algorithm, including probably one approximation, but very fast computations. Maybe we could accelerate using Hamiltonian, or maybe avoiding the Gibbs sampling, maybe trying to sample jointly the images and some parameters without the Gibbs sampling. Could accelerate, but I don't know that.
Yes.
My idea is that depending on a given application, if we do not have fast sampling, switch to Bayesian variational based approach, for example.
Yeah. Thank you so much. I quite understand your answer. Yeah. By the way, would you mind, because the audience are very interested in the paper you showed us, would you mind to send these titles that we can download your paper for the audience?
Yeah.
Thank you. Yeah. Thank you so much.
Yeah, welcome.
Okay. Other questions in the audience? I think that it was really very rich presentation. Many points have been discussed, and hopefully the questions covered some of my questions. But still, I know that very original work that you have done on POTS parameter computation. And can you comment a little more about in slides 16, 17, and 18?
Yes. Okay. Yeah. Yes, this is a standard POTS field. Gamma sub L is the POTS parameter, often denoted by beta. And this is the normalization constant. I just remind that it is a huge summation that cannot be computed as it is. And I'll denote C bar the log partition.
Yes.
Okay. And in fact, what is important is that the POTS model is within what is called the exponential family. And then we can produce, starting from that, the derivative with respect to the POTS parameter of the normalization constant. It is a summation, just derivate this exponential, I have that. And then by dividing by the partition function itself, we have C prime over C, that is the derivative of the log. And then we just have the expectation of this quantity. So it says that the derivative of the log partition is an expectation. And then we can compute the expectation, we can approximate the expectation as an empirical mean. That's just it. And then we have taken a few days of computations to sample a very, very large number of samples of POTS fields. And then for each samples, compute that, just count the number of neighbor pixels with the same value. And then we have an approximation of the derivative of the log partition. That's it, this one.
Yeah.
And we have computed that for various image sizes and various number of classes. This is, I guess, 1 class, 2 class, 3 class, 4 class. And this is varying the size of the image. This is small image, this is large image. And then, given that, that is just computed as empirical mean. Just for fun, we derivate that to have the second derivative of the log partition. And then we numerically integrate that. It is easy, there is no problem. And then we have, by numerical integration of the derivative of the log partition, we have the log partition.
Okay.
And this is interesting in relation with the physics models that is used, that is described by the POTS model. This is, in fact, for very large images, we have a singularity in the second derivative. We have an infinite first derivative that is in relation with fast transition of particle systems. And it depends on the number of class. I think it is 2, 3, 4 class. And it's also more true that we have large images. Is that answer to your question?
Yes. So for a given application and for a given size of the image and for a given number of the labels, we can compute these and then use it.
Yes.
This is the, so.
Yes, it is a kind of brute force computation. Yes. Consider 128 squared images and 250 and 1,000 and 2 classes, 3 classes, 4 classes, and compute all of that on a fine grid. We computed between 0 and 3, 100 values. Because these depend, yes.
But when this computation is done, and then we have the shape of this these curves, then we can use it for specific application that we have. Okay.
Yes. Yes.
Yeah. Okay. Somewhere when you showed the images with missing data, I think that it was 439. Yeah. Here, just a question: do you think that this missing data, if it is more regular, does it change anything? So it means, for example, if we have only one pixel over 2 on the horizontal and 1 pixel over 2 on the vertical side, do you think that this may change the results of the estimation?
In fact, I don't think so, because it could change the sampling of the image.
Because in practical applications, very often we have regular missing data.
In fact,
for super resolution application, for example.
I think also about super resolution. Yeah. In fact, when sampling the images, the textual images, we need to sample what I commented before, a large Gaussian, and the covariance of, or the precision of the Gaussian is a function of the prior covariance, the prior precision. It is also a function of the convolution. Let us forget the convolution. It is also a function of the truncation. And we could think about something regular, as you mentioned, regarding the subsampling of the truncation. Okay, let's think about that. But we have these selection matrices that depends on the value of the current label. So in fact, even with regularity here, as in given regularity of convolution, these breaks the regularity. So I think that even with regular subsampling, I think it will not simplify the sampling problem. I don't think so.
Okay. So
worth checked. Don't know.
Thank you very much. I think that as I mentioned, there is a lot of work behind these slides and this presentation, and I hope that in the future we will have still much more occasion to discuss about some other details, and an application that we are in mind exactly is infrared images. It will be interesting in the future that we can try to see if we can apply this method for infrared image segmentation. This is an application that we are working on just now, and the main idea is that infrared images represents the distribution of the temperature. And we want to segment this image in such a way to know what are the regions of very high temperature, what are the regions of lower temperature, and we want to follow in time the evolution of the temperature in time. So that is why the question of what about the computational cost, but at the other side, the images, infrared images, the size and the resolutions are not very high. So I think that it can be applicable in all cases. Anyway, thank you very much again.
Okay. Thank you for this invitation.
Very rich presentation, and I hope that in the future we can have much more interaction with the colleagues in China.
Yeah, it would be a pleasure to collaborate, and I would thank you again. I would like to mention that an important part of this talk is inspired by the work of Ali regarding segmentation, inversion, and so on. And I will send 2 or 3 papers that are in relation with that. Yeah, just after.
Any other comments or questions? If not,
I want to say maybe this year China is totally open, so we can invite you come to join us for your holidays. If we can make a arrangement in details.
And reciprocally, A few years ago, we have tried to plan you coming in Bordeaux. I remember I write
Bordeaux.
some
Yes.
letters and so on, and then paf, we have been confined.
Yeah.
And
So-
then, yeah.
So now,
Yeah,
now
we
is a
can-
great opportunity. And
Yeah, Go ahead.
yeah, and to
Yeah, I
tell
think
the
that
truth
we
that we have already planned international meeting with Professor Yu and Professor Ali together in Zhejiang province and also in Shanghai. So we choose a good time for you to join us, have a cooperation and also the international conference presentation.
Okay.
Yeah, that was the main motivation of this series of seminars. Was also that we try to make a kind of international cooperation together. Okay, so yeah, for the next for this year, we are planning to organize an international conference, a Woman in Science, and probably during that conference we can also have some cultural activities, and also we, as Ming mentioned, if you can come, and I hope that it will be possible in the future, we can also organize a kind of very close cooperation in the future. Okay, let's see if everybody can show and give it,
Yeah, we make a picture for Su and yeah.
Merci.
Thank you very much, and
Merci. Thank you. Okay, see you soon.
Yeah, see you. Bye bye.
Bye bye. Au revoir.
Au
Au
revoir.
revoir et merci.
Bye.